Hello, everyone. My name is Mustafa Mete, and I recently defended my PhD at EPFL, Switzerland. I'm not sure if I can use the doctor title yet officially, but it's already feeling good. So today I will talk about SORI, a softness rendering interface to regenerate tactile sense of softness. This work was recently published in PNAS, and yeah. So I like to start with a interesting AI-generated image that is, I think, relevant. So what you see here, a marble surface. So a hand is touching on a marble surface. So this could be as an art, but also if you pay attention to the fingertips, it also looks like hand is touching a soft surface. And this is interesting. This is why I think the haptics is important, because really without touching things, we might not get the full information about our surroundings. So particularly in this work, we focused on a sense of softness. So this sense is very crucial for survival of both humans and animals. So we get so much information thanks to this sense. So for example, by pressing an avocado, we understand the ripeness of the avocado, freshness of a bread, or medical doctors use for palpation to detect the tissues, if there's a tumor or not. And also we commonly use it during our social interactions. So this sense is very crucial, but how does this work actually? So previous study pointed out that the sense of softness coming from both cutaneous and kinesthetic cues. And so more particularly, so on the fingertip, it really depends on two main cues, the contact area and the stiffness. So what you see on the left, a fingertip is touching on a soft Turkish delight, and it's kind of like a marshmallow. When you press it, you can see that the finger is going deforming the surface, and the contact area is quite large, but we still feel low stiffness. Then in the second case, if you put a hard biscuit on top, we can still feel its low stiffness, but our fingertip can separate these two. And it's because this time we have lower contact area with the surface. So lastly, imagine you are touching an aluminum block. So this time you both feel high stiffness and small contact area. So, and fingertip can separate them really well. And what we wanted to do, we wanted to create a haptic interface that can create that can generate the contact area and stiffness independently. So here you see SORI, and it's mainly composed of two parts. On the top right, what you see, the contact area rendering part, basically it's a half toroidal SPA, soft pneumatic actuator. So when you inflate the SPA, it covers your fingertip and it controls the contact area. So there are a few things important here. So this structure made with soft silicon membranes, very thin membranes. So the softness is crucial here because thanks to the softness, it can adapt to different fingertip shapes, and also it can match the compliance of the fingertip. Second, the toroidal shape is important because when we press the surface, we don't want this contact area rendering part to apply normal forces to your fingertips, so that we can decouple the contact area rendering part from the stiffness rendering part. And at the bottom right, what you see is the stiffness rendering part. Basically, it's made with a folding-based prismatic joint, and inside there's another pneumatic actuator. By controlling the pressure inside, you control the stiffness of the overall structure. And in the structure, we have embedded force sensor and the position sensor, so we can close the loop when we control the softness. So this is great, but next question is, we have a haptic interface that we can control these cues independently, but how can we regenerate the actual softness of a surface? So, and for that, I like to talk a little bit about the subjectivity in softness perception. So currently, when we evaluate the softness of a surface or haptic interface, we really count on the user studies. And usually they are highly subjective. And this kind of, I was thinking where this subjectivity is coming from. And it reminded me of this dress. It was quite famous a few years ago. I don't know if you remember this one. And the question is it yellow or blue? So some people see it as yellow, some people see it as blue. And the reason turned out, so even though the reflected light frequency is the same, people have different thresholds, right? And so this brings me to this question. So how can we quantify and estimate softness cues in personalized manner? So because everybody might be feeling different softness as well. So I did a few tests to a bit understand what's going on. So here I conducted a stiffness experiment where I touched a soft surface with different indenters. So here what you can see, so we have a cylindrical indenter, spherical indenter, and there's another spherical indenter, but this time it's a smaller radius. And when you look at this plot, the force displacement curves are quite different. And actually the curve is giving normally the stiffness. So it just shows that maybe the perceived stiffness is different for different fingertips. And second, so I run a contact area versus force test. So I designed an experimental setup where we have a linear guide. So you put your fingertip on it, and we have a highly sensitive force sensor. We put ink, you press on it until you reach the certain force. And by using the ink method, we capture the total contact area versus the force. And so here I just showed an example for two subjects at different forces. As you can clearly see, the contact areas are completely different. It's because the subject 2 had much smaller fingertip. And it just shows that the perceived stiffness and contact area really depends on mechanical properties of the fingertip, such as shape, size, and the stiffness of the fingertip itself. So here, this is the summary of our softness regeneration method. It's composed of basically 5 main parts. First, identification of fingertip parameters, identification of surface parameters, estimation of softness cues, and then we mapping these cues to the device. So I will just briefly mention each step. So how do we identify fingertip parameters? So for that, we run a basic experiment where we ask people to touch a flat surface, flat rigid surface, and we collect the contact area and force. And I also developed an analytical model where I use nonlinear finger pad stiffness model. And I'm also using Hertz contact model. And by using this data, we are running some regression to estimate the fingertip parameters. And what are those parameters? The radius of the fingertip and the Young modulus, nonlinear Young modulus of the fingertip. And here on the right, you see the plot. So after estimating those values for 2 different subjects, we can estimate well the contact area at specific applied force. So this is cool. And how do we identify the surface physical parameters? It's fairly simple. We use the shore hardness of the surface by using some durometers, and we also get the stiffness using a universal testing machine. And we send this information to the haptic interface. And for the estimation, again, I'm not going to go into too much detail of the math here, but we used Hertz contact model for soft indenters and soft surface contact. And we estimated the contact area, total contact area, and the force for given indentation depth. And we used those values. And again, we developed some analytical model for the device. We calculate the control inputs. In our case, the pressure 1 and pressure 2 going to the soft pneumatic actuators. And here you see the results. So on the top, we touch a soft surface, and as you can see, when we touch the device, so it's inflating, and then it's covering more area on the fingertip, and at the bottom. So as you can see, it's the toroidal space is not very much inflated, and also the bottom part is a bit stiff. So and on the right, you can see our quantified data. So, but these are homogeneous surfaces, and we ask ourselves what else we can do. So we also show that we can use this haptic interface for heterogeneous surfaces. So what I mean by heterogeneous surfaces, so the top layer is soft, bottom is hard, or vice versa. And we used it for our daily objects. So we tested a bunch of different foods, marshmallow, bread, salmon, and some beef, and no food was wasted. We ate them all. And finally, so those were all static surfaces, but we also showed that we can use it for dynamic surfaces. So here, what we have a heartbeat model, and we showed that thanks to this embedded sensors on the device, we can not only create this the softness sensation, but also we can also give the heartbeat sensation to your fingertip. Where can we use such devices? So there are many possible applications. First, like it can be used for online shopping. Imagine you want to order your avocado from your favorite online website, and normally you don't know what you are getting. But what you can do, you can touch the object thanks to this haptic interface before you buying, and then you can understand if it's good or not. Or second, currently the medical palpation training is based on just the experience, so medical doctors touch and learn. But we can, if you know what's the softness or hardness of this tissues with a tumor, so we can already train the doctors. And many other fields, as I said, like it can be used for teleoperation, exploration, and many other possibilities. So in summary, we tried to achieve a softer and more realistic interaction with the haptic interfaces. I developed a haptic display that can decouple the contact area and stiffness. I developed analytical models to quantify and estimate the softness cues, and a method to regenerate the personalized softness cues. So what's the future right now? So we are working on, so currently the fingertip calibration process is separated from the device. So we first calibrate, then we send the data to the device, but we want to integrate both. But for that, we really need high resolution contact area sensors embedded in this compact form factor, which is a bit challenge. And we are trying to make the device multi-degrees of freedom rather than just 1 degree of freedom, because we don't perceive softness by just tapping. We also apply shear sometimes to understand. And so we also want to add more modalities to the device, such as like a vibrotactile feedback. And with that, I'd like to thank to my co-authors and our funding sources, and thank you for listening.
All right. Thank you very much for the nice talk. Is there a question from the audience? Yeah. Okay.
Yeah, go ahead. Okay. Fantastic work. I didn't catch how you quantified like whether or not this was actually giving the sensation to the person. Like did this actually, so you said it's subjective, and I like the idea of combining both the surface area and the impedance. It's brilliant. So my question is, at the end, was there a way to quantify whether or not the person was actually perceiving the target object or not?
Oh, thank you. This is a really great question. So actually, we didn't run user studies to evaluate what's the sensation. So what we tried to do, we tried to push to quantify the cues that are affecting the perception, and we show that quantitatively we can regenerate them. But actually, it's more than that. For example, like many other studies show that even like your memory affects the sensation or the vibrotactiles perception. So what we try to do, so even if we run right now, we don't know if it's because of the device or because of the memory or because of the mood, etc. So our goal is to just push more towards this kind of approach in generating. Yeah. Yes. Yeah. In the future, definitely. So we know that right now there are some cues are missing. So once we show that we quantify all of them and we put what we know that affects, then running experiments help a lot. Actually, also we need to conduct some so we want to run some collaborative projects with neuroscientists in the end to better understand what's going on so that we can update the device. So it's kind of a loop, right? So we better understand how it works and then we improve the device, etc.
Yeah, very nice talk. My question is about the material that you use for your device. I suppose it's silicone. And how much do you think so we expect the silicone to be soft, but then can the illusion work with another material, or because we expect to be soft, so is it really helping the sensation?
Yeah, definitely. This is also a great question. So we are using silicon, that's true. And more specifically, we are using Dragon Skin 10. And we didn't optimize the material, and it's affecting a lot actually. So actually, ideally, we want to use the softest and thinnest material as possible, so that when we press, we don't feel any normal force. So right now, we still have some small force, but we show that it's kind of negligible compared to stiffness that we are generating. But so that's the ideal case, and there's a lot of room for improvement and research in that area, the which material. And also, like another question, can we embed some sensing in that material as well? So yeah, thank you.